Hi everyone, this is JF with you today to discuss continuous random variables. We have moved on from our previous section, which was approaching discrete variables. A variable that is continuous cannot be treated in the same way as a discrete variable. For example, how do we even approach probability distribution tables for a variable that has infinitely many different outcomes? For example, suppose Awa is waiting for the 124 bus at the corner of Sherbrooke and Claremont Streets. She starts her stopwatch and will stop it whenever the bus arrives, makes a full stop, and open its doors. If you consider calculating the time with extreme precision, every possible outcome of this experiment becomes very unlikely a priori. In other words, there's very little chance that Awa can guess to the precise decimal the arrival of the bus. So rather than discussing probability tables, we will use a perspective of density functions to compute probabilities associated to the variable's outcomes. More specifically, we will associate area under the density function to probability. Here are the properties of density functions. If x represents a continuous variable whose support is s, then f of x is a density function if it remains non-negative for all x in its support, if the entire integral on its support equals 1, and when these conditions are satisfied, then the probability that the continuous random variable x will be found between a and b is equal to the area underneath the density function between a and b, in other words, within the integral. Since a density function is greater than 0, then the probability, or in this case the definite integral, corresponds to the area under the curve, and it represents probability. Only intervals can generate non-zero probabilities. This means that the probability of an individual value taking place for a is 0. As a second note, the boundaries individually do not hold any area, and therefore being included or not from the integral makes no difference. In other words, all of these different probabilities are equal to one another. When it comes to calculating expected value, variance, and standard deviation for continuous random variables, then, rather than having summations, as we did for discrete variables, expected values will be the result of integrals, where x multiplies the density function. Variance will be obtained from the integral, where the difference between possible x values and the expected number are squared and multiplied by the density. As usual, standard deviation is the root of variance. All of these integrals take place over the entire support. For example, let's assume Awa is still waiting for the 124 bus, and she will count time as we mentioned earlier. Let us denote by x the time of arrival of the bus as shown on Awa's stopwatch. Let f of x equal 1/5 minus 1/50th of x represent the density function for her waiting time, and x will be considered to be between 0 and 10. f of x is greater or equal to 0 for all x, as the following graph demonstrates. Secondly, the entire integral of the density function on its support is 1. In fact, if we integrate from 0 to 10 the density function, then the outcome will be equal to 1 as it should. In Awa's experiment, the expected value, variance, and standard deviation can be calculated by the formulas that we stated earlier. The expected value is the integral of x times the density function. In this particular case, we would need to use expansion and the power rule to calculate the definite integral. The outcome will be 3 1/3 minutes. So basically, we would expect Awa to have to wait 3 minutes and 20 seconds. As for variance, then the calculation is much more elaborate, as we will need to expand a lot more. The outcome of this integral, 50/9, represents waiting time squared. And, as usual, making sense of these units is more appropriate when we root the answer of the variance to obtain standard deviation, 2.35 minutes. How likely will Awa have to wait more than 4 minutes? This probability can be calculated by integrating between 4 and 10, 10 being the end of the domain for the support. The area underneath the curve between 4 and 10 will provide us with the probability that this event will be realized, in this case 36%.